Hey everyone, my name is Kendall. I am the product manager of a project called Cowrie. We're building at Cowrie is a decentralized technical support and knowledge sharing community. And so I titled this talk, Building a Complex Decentralized Application. Obviously everyone's pretty much presented is quite complex. So really what this talk is going to be about is kind of how we sort of reasoned about how decentralization could fit into our project, and then how we constructed the architecture around that. So hopefully be a couple of interesting things to touch on. So really when we decided we wanted to dive into this, we wanted to kind of first evaluate the different levels of decentralization available to us. So just going through those quickly. So fully decentralized, as we saw it, is basically having every single bit of data being served in a peer-to-peer fashion. So this includes having your static files that compose your front end being served via Swarm or IPFS directly to the browser, and then all other business logic and data is encapsulated in smart contracts or peer-to-peer systems. So it's currently pretty difficult to actually do that. So one thing we see as only a slight trade-off is serving your front end via something like S3 or a content delivery network, and then having all of your code be completely open source for evaluation, and then maintaining your backend in a similar way. One step down from that is basically deciding which part of your application is absolutely critical to be composed in a completely decentralized way. So which data and business logic of your system are really critical for somebody to replicate what it is that you've built, and then making a few trade-offs around that and building some sort of more centralized caching, for instance, or supporting services. So moving another step down, and really what we saw is kind of the last level of maintaining any sort of decentralized system is where you have a pretty standard client-server setup, and you choose some small specific portion of the application to use the blockchain for. A common use case of this would be something like payments. So moving on from that, we then were thinking, okay, these are the options available. What does decentralization mean for our project? So to give you a bit of context of what it is that we're building. So we're building a community-based technical support and knowledge network with a built-in incentivization system, and all of this is going to be built on top of Ethereum and IPFS, and we'll get to that in a second. So the MVP version is basically going to be a bounty system to incentivize the creation of tutorials and how-to articles around different topics in the ecosystem, specifically like technical implementations and libraries, and then tipping to reward the authors and the experts who have created this content. So here are just a couple of screenshots of the project we've been working on. But getting to our goals. So what we wanted to do is lay out what our goals were and then think of how decentralization could help us achieve those goals. So first of all, we want to be supportive of open source software. We want to be community owned pretty much as possible. We really want the data to be owned by those that create it, which is going to be the community in this case. We want the application to be extensible, so we want it to be very easy for other developers or community members to build on top of the platform that we've created. We want to be organized and searchable, so we want it to be easy to find the information that you're looking for as a user, especially since this is going to be in a technical support kind of fashion. We want to be up to date, so we don't want any sort of out-of-date documentation or tutorials. We find that it can be quite harmful if you're going through a walkthrough and you realize half the way through that it's using an outdated version of the library or something like that. And then we want to be rewarding for contributors. So how does decentralization help us achieve these goals? Well, one of the most important aspects that we see is this idea of the community ownership of content. So by storing as much of the information and the content on-chain and in IPFS as possible, we can really make it community-owned, and that we're not the ones who sort of control the access to this content. There's also this security of existence. If, for whatever reason, we were unable to continue to maintain the project, the data would still live on past whatever we were able to do, and another team or community member could come along and continue working on what we built. One of the things we're most excited about with Web 3.0 is this idea of an open by default API. So what we mean by this is that anybody can kind of come in, build products on top of what we've created, and then they also have the agency to create useful sub-communities for any of the content they find that they think they can group together in a better way than we did. And then of course you get the relatively trustless interactions and payments that something like Ethereum can enable. So once we kind of had these sort of tools and our goals in mind, we started thinking, okay, how do we design this system? How do we make this work? So we ended up choosing this third kind of level of decentralization that I laid out. We were basically like, we want the content and the business logic to be all completely fully replicable and all living on chain and in IPFS, but we're okay with having some supporting services around that, like using caching so that we don't have to make calls to smart contracts in order to populate the data every time and to make things fully searchable. So here's a bit of an overview of our architecture, which I'll be walking through. So the things that we've decentralized, the actual creation, the requesting, everything related to these bounties, like requests for this content, and the actual storage of any of the content that's generated is going to be handled in our smart contracts and stored on IPFS. So all of the content is going to be referenced on-chain in our smart contract with the author's address and the IPFS hash. To support that, we built a couple of little tools here, one of which is what we're calling a broadcaster. So this broadcaster is basically a generalized event subscription service. In addition, we've created, well, so when we store a document in IPFS, we actually create two documents. So we create the actual content document itself, and then we create a reference document that has things like comments, upvotes and downvotes for the article, the history of the article if there's been changes in the content. So it's basically links to the old hashes, and then an audit log. So the reason that we created this document is because we wanted to keep the actual hash of the content itself as static as possible. And so if you know anything about IPFS, every time you basically write any sort of data to it, you're going to create a new hash because you're actually just hashing the content in that document. So this enabled us to basically store almost a permalink to the content on chain without having to do a transaction every time we wanted to update the content. Another trade-off we kind of made here, we created this idea of a topic owner. So for the different projects that are going to be hosting on our site, we wanted to basically solve the curation challenge by designating one of the maintainers of a particular project or topic as sort of the final arbiter of the content that's going to be stored on the system. So an example of this is MetaMask, who will be hosted on our system. So they will be the sort of the final deciders of what kind of content is going to be going under their tag. We do want to phase this out as soon as we can, so we are working on a reputation system and a voting system to make this a more community-based approach, but this allows us to keep the quality of the content high from the outset. Another thing that we're doing here that's kind of a semi-centralized way, so for authentication, we're using a pattern where we issue a JSON web token against an Ethereum address, and we use a really interesting feature by MetaMask where you can sign an arbitrary piece of data so that you can then basically validate that person holds the private key for that address, and this allows us to have a passwordless login. So this is actually a pattern you can see quite frequently. I think CryptoKitties uses something very similar, which we think is very exciting. So moving on to the more centralized portions of our system. So mainly the things we centralize are around caching the content that exists. In particular, we are caching the IPFS articles in Elasticsearch so that we can have full text search for our application. So we are going to open source this code because we do want this to be fully replicable by anybody who wanted to build an additional front end related to our system. Another thing we're doing in a very centralized way now, unfortunately, is notifications. So because of the very asynchronous nature of what we're building, we really just needed to keep people notified in some way. So we just decided to use very straightforward email notifications. And we are storing those email addresses in MongoDB right now off-chain for the time being. So I'm just going to briefly touch on the entirety of our stack before kind of walking you through the lifecycle of our transactions and then how that touches each part of our stack. So on the back end, we're using Java, we're using the Spring Boot framework and Web3j to interact with the chain. Document storage, as I've mentioned, is done in IPFS with some caching in Elasticsearch. For the middleware, which I'll actually get to in a minute, we're using Kafka in a kind of interesting way to basically help with using IPFS as a document store. For the Ethereum client, just Geth and a custom broadcaster, which is also built in Spring Boot. And the front end, we're using React and Redux and Web3.js. So walking through a transaction here. So I'm basically just going to describe how a user creates a bounty and then what that looks like on our system. So let's say that a user is requesting an article, probably by attaching some ether to this in a bounty. So an API call is going to be made, which is going to then return a unique identifier for this request. So then the front end is going to make a transaction call to our smart contract referencing this unique identifier. And the broadcaster, which is that event subscription service I mentioned, is going to be listening for those events. And when it receives one of the events, it's going to use the UUID to look up the data in our database, and then it's going to reconcile the event data with the data that we expect to be in that event that we've already stored on our side from the previous API call. So once that happens, we're then going to send two messages eventually to the front end, basically to notify the user that the transaction has been mined and included in the first block, and then also after the 12th confirmation. And the reason for this is because that's when we consider it completely fork resistant, and we have some behavior that then becomes enabled as a dependent on that 12th confirmation. So moving on to how we're using IPFS as a document store here. So I'm going to walk through two different user flows here. So the first of which is saving a draft article. So we actually decided to keep this functionality off-chain, and the reason for that is that well, it's not necessarily a finalized piece of content. This might be something that a user's just, like editing a document. They may want to submit it, they may not. So we didn't want to force them to do a transaction since they might never actually like receive any sort of bounty payout for this or have the ability to be tipped or even included in our content. So the user starts and saves a document, and that's going to make an API request with the document content. So then the backend is going to create two of the IPFS documents here. That reference document that I was discussing earlier, and then the actual, what we hope is going to be the long-lived content document itself. And then the reference document data is going to be saved in Elasticsearch for the time being. So the corresponding transaction here is once the user basically decides, okay, this is a piece of content that I'm satisfied with, I now want to actually store this information on-chain. So the way this is going to work, the user is going to submit this final content, and this is actually just going to do a transaction direct from the front end containing the IPFS content hash of the content that they want to submit. So because of that topic owner user type we have right now as this sort of curator, the topic owner is going to receive a notification letting them know there's some content ready for approval. So once they're happy with the content, they're also going to make a call to our smart contract with the IPFS content hash, and then those two hashes are going to be compared in the smart contract. And it's either going to accept it or reject it, depending on whether that test passes. So the reason that we created this test is because of an attack vector we realized where a user could basically submit any sort of, if they were just interacting directly with our contract, they could submit any arbitrary IPFS content hash. And if we did not have the topic owner also submitting an IPFS content hash, then they may not realize what it is that they're approving, which is why we came up with this functionality. So while we were doing this, while we were using IPFS as a document store, we uncovered a few, one in particular consideration that we wanted to mention that you should be aware of if you decide to do something similar. So in that create request function that I mentioned before, it triggers two events that we're listening for. So there's this request created event, and then there's this bounty updated event. And so both of these events are going to first do a GET request in IPFS and basically look for any content that already exists. If it exists, they're going to take that content in that IPFS hash, and they're going to then add whatever it is that they're going to write after that. So the problem that arises is because we are doing this, we have multiple sort of services set up for scalability. It's possible that these two events could occur at more or less the same time. And so the reason that that's a problem, well, since the nature of IPFS, it basically creates a new hash every single time. There's no real locking functionality here. And because both of these events are going to be doing this GET request first, checking if this IPFS hash exists, and then pulling the content to append to it. Well, if that content doesn't exist because they're both happening at the same time, so neither of them have this like pre-existing IPFS hash, then one of them is essentially going to win and overwrite the other, and we're going to lose whatever content would have existed from that corresponding event. So to get around this, we had to come up with some sort of locking functionality. So what we decided to do was use Kafka. So Kafka is really helpful in this situation because we can basically confirm that a single service is always going to read from a single partition of Kafka. So what this allows us to do is because we have this unique request ID for each of the requests that are occurring, if there are multiple events for a single request ID, they're going to be sent to the same partition of Kafka. And then because this Kafka instance here is going to be processing them in a single threaded way, they're going to go one after the other. So if the second is doing a GET request to get the content and then is going to be appending to it, that content is definitely going to exist. So this is basically us recreating some locking functionality that exists in most standard databases. So the second one is a bit of an aside from this. This is actually just about some of the user experience considerations that we've discussed after just interacting with as many of our potential users as possible. So the main one here that we came up with, we really decided we want to limit transactions to direct transfers of value as much as we possibly can. That's the main reason that we decided to make the comments and that editing back and forth flow off-chain, because we really want the user to be either sending a transaction in order to be able to win a bounty, in order to be able to create a bounty and then get some content in exchange, or as a topic owner, to have somebody creating a really good walkthrough for the project that you're maintaining. We see all of these as direct transfers of value. We also decided we really need to make sure that our users are informed of all the confirmations. We want them to know when the transaction has hit Infura. We want them to know when the transaction has been mined the first time. And then we want them to also know when they can actually use the behavior that's dependent on that transaction being confirmed the 12th time. And we want to keep them involved each step of the way. Sort of analogous to this, we wanted to minimize any user experience blocking that happens during confirmation time. We did not want to ever stick the user with just a spinning wheel and make them wait for this transaction to be confirmed, especially because we let them set their own gas costs. It's impossible to tell how long it's going to take for this to happen. So just to wrap up, I make this really quick. So the things that we decided we needed to do. First, before we got started on this project, we wanted to define decentralization and how it can enable and improve the existence of our product and serve our users. We wanted to evaluate the different trade-offs we needed to make, both on, like can we put on-chain, what do we need to keep off-chain. We decided to develop some supporting services because we realized that not everything needed to be on-chain in our case, and there were some ways that we could use caching to really just improve the user experience. We wanted to minimize the user cost and keep transactions only to value transfers, and then we wanted to minimize any user experience blocking. All right, guys, that's pretty much all I have for you today. So that the way we're using IPFS, we actually has open sourced this bit of code. So if you guys are interested, please check it out on GitHub. And if you have any questions, please come ask me or Craig.